So this is a quick recording to try and help us prepare. There are some mistakes on this practice test, and I may or may not have told you if you were in class. Some of them, I'll mention them again as we go along. So section 4 starts out with just factoring. Okay, so if we are just factoring, the first one we're going to factor is 4x to the 5th plus 32x squared. So the first rule of factoring is to take out a GCF. So I'm going to do that. I'm going to take out a 4 and an x squared, leaving me with x to the 3rd plus 8. Now you want to look at what we have left, and we want to decide, is this able to be factored further? And we did have a new strategy with sum or difference of perfect cubes. And so we're going to use that next. So we keep our GCF out in front. When you have a perfect cube, you get a binomial times a trinomial. So you have to think about, what are they perfect cubes of? Well, x and 8 is 2 times 2 times 2. So yeah. Next we have the perfect square of the first part, the opposite of their product, and the perfect square of the last part, which happens to be a 4. Okay. For the other one, there was an error, possibly. And so I changed that into a 2z. So that is 1, 2, 3, 4 terms. There is no GCF, so I can't use GCF. And since there's 4 terms, we're using what we call grouping. So grouping is where I can do the GCF. I do 1/2 at a time. So I can take out a z squared from the front half, leaving us a 2z minus 3. The back half, it doesn't look like I can take anything out. So if this would have been a minus sign, I'd be taking out a -1 as is. I'm just going to take out a +1. Having that be negative would have helped in a couple of other ways also. I didn't want to change it again. So then we would have z squared plus 1 times 2z minus 3. If this would have been a -1, well, it was a difference of squares, we would have had a z plus 1, z minus 1. But the way that it's written, it was just grouping. Okay, chances are going to have more than one strategy since this is second semester. On number 2, according to the directions, it says that we will show that x plus 3 is a factor. So if x plus 3 is a factor, that means I'm going to use a -3 out in front of my synthetic division. And I put my numbers in order from least to greatest, so that's a 3, and a -3, and a -36. And we're just going to start working with this by bringing the 3 down. Then I multiply 3 times the -3, becomes a -9, and I add down to get a -12. And when I multiply the -12 times -3, I get positive 36. And when I add down, I get 0. So this right here is showing that I have a factor because there was a remainder of 0. It says then factor completely. So we want to show all the factors. So at 3 really means I have 3x cubed minus 12x squared. And I want to factor this more. So to factor that more, I'm going to take out the GCF, which is a 3x squared. And that gets us an x minus 4. So my final answer is this 3x squared times the x minus 4, and we have to include that polynomial function completely factored still has that x plus 3 that was in that set of directions. Okay, so that's what we're looking for. If they had said solve completely, possible, then you would have had x equals 0 from the 3x squared equals 0. X minus 4 equals 0 would leave us with an x equals 4. And x plus 3 equals 0 would leave us with -3. So if it would have said solve, so you should be prepared to factor completely, possibly solve by factoring. Okay, I'm just going to erase that because that's not what it says. All right, so I did skip a problem. There was like a number 2 and then a number 4. So there's definitely another problem missing in between here. It's either going to be a solve by factoring problem, or it's going to be a list all possible rational roots. So that could also fall in here. So the rational root theorem, I'm going to put this one in here for this particular problem, means that you take each factor of the last divided by each factor of the first. So in this particular problem, I'm going to be taking 1s and 5s divided by 3s and 1s. So 1 divided by 1 and 5 divided by 1. And I have to divide them by the 3 because that's what we get if we list all these out. So it becomes a positive or negative 1 over 3 and 5/3. So if we were asked to do that, that would be a possibility. However, the question actually says to predict how many positive, negative, imaginary. So if x is a positive number, then this would be a positive term, this middle term is negative, and the 5 at the end is positive. So we look to see how many times the sign changes. So the sign changes once, twice, so we'd say 2 or 0, positive, real zeros. If you can subtract 2, you always should. Okay? Then we're going to consider if x is a negative. If I take a negative to the 5th power, that's negative. And that positive 3 times that negative is a negative. And that's the same idea. If I take a negative to the 4th power, that's a positive, times negative 7, that's a negative. If I take a negative to the 2nd power, that's positive, times negative 2, that's negative. If I have x is a negative x, and we're subtracting it, minus a negative, or a negative times negative is the same as a positive, and that 5 stays positive because there's no way to change it. There's no x there at all. And we can see that the sign changes one time. So 1 negative real solution, 1 negative real root, or we would expect our graph to cross the x-axis on the negative side one time. Okay, and then we have the imaginaries. So according to the fundamental theorem of algebra, the highest exponent here was a 5. That was higher than all the other exponents. So that's how many total answers I could have. Completely total distinct zeros. So 2 plus 1 is 3. I would need 2 more to get to 5 total. Okay? So again, I was looking for this idea that they had to add up to 5. I have another option though, because I could have, oopsies. Where was it at? I could have 0 of these, 1 of these, and a different number. That's going to have to be a 4. So if we're looking for Descartes' rule sign, this is what we're looking for right here. Technically, we don't need the 5, but it doesn't hurt. Okay. On this one, it says you may want to use all of these other ideas, and it's really up to you what all you choose to use. So if I wanted to use the rational root theorem, I could definitely do that. I would, for the rational root theorem, RRT, I'm taking plus or minus factors of 12 divided by factors, well, it doesn't look like a number, so it's a 1 right there, which is just a 1. So realistically, it's a positive or negative 1, or 2, 3, 4, or 6, 12. So I just listed all of the factors of 12 and I divided them by the 1. So that's my rational root theorem. If I were to do Descartes' rule of sign, especially the positives or negatives to help me narrow down my options here, what I would do is for Descartes, a positive and negative. So if it's a positive, it's going to go positive x to the 4th, positive, positive. So I don't see the sign change at all on here. So we'd say 0, positive real number. So that list that I made, I shouldn't even try any of the positive numbers on it. Waste of my time. Okay. If I let it be a negative, we'll see how many we should expect there. And as that turns out, that's a positive, negative, positive, negative, positive. 1, 2, 3, 4. So there's 4 or 2 or 0 negative real roots. Okay, and the degree was 4, so there could be 0, 2, or 4 imaginary, but we're going to focus on the real ones. Primarily. Now, what I already did was I went ahead and I tested the numbers to see which of these numbers that I have listed up here will turn out to get me a 0 if I replace it. I substituted it in for the x's and evaluate it. I wanted to know if I was going to get a 0. Is it going to be on the x-axis? And what I found out was that the numbers, where did it go? I think -1 worked, I think. And I can always retry it. -1 worked. -2 did not. -3 worked. And that's enough to get me started. I don't believe anything else worked. Nothing else worked. So really just these two answers worked. And so I'm going to use synthetic division like we did before, only we're going to do it over and over again. So 1, 4, 7, 16, 12. I'm going to put -1 in here first. So the first number always comes down, and then we multiply and add. That's a 3. That's a really bad 3. And zoom in to write this part. And we add, and multiply, and I add. And the whole idea is if something is a factor, that means you have a remainder of 0 that divides it evenly. Okay, so that's definitely a factor, and that's good. Okay. So now I'm going to try the other number. The other number that worked was the -3. So I'm going to put that in here because I don't have enough to use the quadratic formula at this point in time. I don't want to start all over because I'm not getting a smaller number or polynomial to factor with. And as it turns out, I again have a remainder of 0, which does prove another way to check to see if that's a 0. That is. And so since I start out with an x to the 4th power, every time we divide, it takes a power away. So this would have been like an x cubed, which I can't factor. Actually, I could have factored that. Interesting. And this would be x squared and 0 x's and just the number 4. So what I'm looking to solve right now is x squared plus 4 is equal to 0. I want to know equals this to 0. Now, if it was a -4, I could use a factoring. As is, I could also still use the quadratic formula, the opposite of b, plus or minus the square root of the quantity of b squared minus 4ac, all over 2a. That's an option once we get down to quadratic. I'm going to go ahead, since there's not a trinomial here, I'm just going to go ahead and solve it using the square root method. So I subtract the 4 to the other side, and then I have to square root, allow for both positive or negative, and the square root of -4 happens to be 2i. Whenever you multiply, square root of negative, you get an imaginary. So the final answer for this problem is that we have -1 as an answer, we have a -3 as an answer, we have a 2i as an answer, and we have a -2i as an answer. So it was a 4th degree polynomial function, noted by the highest exponent, and we did get 2 negative real answers and 2 imaginary answers. That's what we'd be looking for on this one. Okay. All right. So this one is working backwards to try to come up with the polynomial function. So if we're told that -5 is, in fact, a root, then we're going to have the factor of x plus 5. If we're told that 1/2, we're going to write that as x minus 1/2. And we were told that 3i is going to be x minus 3i. Whenever you have an imaginary or a square root, you're going to have both of them. It's always plus or minus the square root. So this is going to turn into being an x plus 3i also. So a couple of things we're going to do. first thing is we want integers. So if I have a decimal or a fraction, we're going to multiply to get rid of it. So I'm multiplying both of these terms by a 2. It would come out when we're solving. Trust me, it works. And I'm going to go ahead and multiply these last 2 together that have the imaginaries. So I'm going to have an x squared plus a 3xi minus a 3xi and minus 9i squared. But what we know is that I squared is really a negative 1, so that's really like having plus 9. And those other ones disappear. I'm also going to multiply this beginning part very similarly. So I have 2x squared minus 1x plus 10x minus 5. Okay, and simplifying that, I now need to take this trinomial times this binomial and simplify that. So I'm going to have my function being 2x to the 4th plus 18x squared plus 9x to the 3rd, 81x minus 5x squared minus 45. Any like terms, you want to put those together. Highest exponent first is the 4th. Any cubes? Yep, a 9x cubed. Any squared? We do a negative 18 and a negative 5, so that's 13x squared. And x is 81. And numbers, just that negative 45. So this is what we come up with as our final answer to that polynomial right there. Okay. If we are going to describe them as even, odd, or neither, what we do is we replace the x with a negative x and compare the signs of each term. So if I make this a negative x, very similar to what we did with Descartes' rule of sign, we could come up with this. So anytime I take a negative to an even power, it's just positive. So these two stay the same so far. This one changes though, 8 times a negative. So if these right here are exactly the same, we would say it's even. If they are exactly the opposites, we say they're odd. So I have a 3 and a 3, that's the same. This is the same. Oh, that one's different. So it is definitely not even, nor is it odd. So we would say this one has to be neither. Okay, we're going to do the next one the same way. Replace all of the x's with a negative x. So if I take a negative to the 5th power, that's going to be a negative. If I take 7 times the negative, that turns out to be a negative 7x to the 5th. This right here stays a negative 12. Excuse me on that one. I wrote the wrong thing here, so this is what that was cubed. So a negative times a negative is positive, and then a negative 11x. So we want to compare these to the original. That's the opposite. That's going to be the opposite. And this term is the opposite as well. So since every single term is the opposite of the original, we say that that original function is said to be an odd function. Okay, odd meaning 180-degree symmetry with respect to the origin. Okay. The next one is to analyze the graph. And so if I want you to do this, we're going to be possibly estimating decimals for these values. So the degree is going down, up, down, up, so that's going to be a degree of 4. The zeros, we look at where it crosses here, and it's really hard to see the graph on this one, but it looks like it's a little bit past the 1 and a little bit right before the 2. So I'm going to say my zeros happen when x is about 1 1/5 and about when x is roughly just before the 2. Are there any local max or min? So that means we're looking for like these high points where it changes directions from increasing to decreasing or going up to going down. We definitely have one of those. And that looks like it is less than 1. So I'm just going to say at 8/10. Looks like it's more than half, but less than 1. And if there's any minimum, so we actually have 2 minimums here. One of them, to me, appears to be right on the y-axis at 0. The other one, 1, 2, almost at 2. So I'm going to say about, 1 1/8. That'll work. So just analyzing where those are at. Same idea with this table of values. We want to analyze where those are at. So the first thing I would analyze is the zeros. So we're looking to see if there's any zeros here, and there is one. That 0 is right here. So this right here is a 0. So I'm going to go and say when x equals 2, I have a 0. Anywhere else would be like if it changes sign, 2 numbers in the y column, the function column, might change values from a positive to a negative. Oh, there's one. So here it went from a positive 2 to, or excuse me, a negative 2 to a positive 3. So I'm going to have a 0 in between there. The other ones are all good to go. So I would say between x equals negative 2 and x equals negative 1. All right. To look for the relative mins and maxes, we're going to talk about where it changes direction. So it's going up from negative 5 to 2, still going up, and then it starts to go down. So since it just changed right here, this is a turning point, and it was going up to down. So go up to down. That's going to be a maximum at that value when x equals 0. From 4 to 0, it's still going down, and here it's still going down. So technically speaking, we only have the one max or min, and if my graph's going up then down, it's really only a degree of 2. Really just a degree of 2, or you could kind of sketch it out or graph it out if you wanted to. On number 10, the example I have here doesn't turn out very well, and so I came up with another one I think is going to work. We want to find the finite differences, so I'm subtracting the first number from the one after it. So 10 minus 5 is 5. This is a 13. 49 minus 26. 46. I believe. I think I had a different number before. It is a 46. And from there to there is 72. So I may have to be changing a number somewhere in order to make this work. Okay, so that didn't work. This right here is going to be an 8. This is a 13. This right here is 20. And this right here is 26. That's 5. That's 7, and that is 6. Okay, so that did mess with me. I changed a couple of numbers. But if we were to pretend that I didn't change those numbers that way, and let's kind of override the system. If on this row they were all 7s, then we'd say first, second, third. The degree is 3. The original didn't have one, and I may try to change that. But a couple of things to consider, again, for your Chapter 4 assessment. We're just getting started, and there will be some things that will be different.